Hello everyone, I'm Pranali Surkar. I'm working as an assistant professor in the Department of Electronics and Communication Engineering at Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. So I welcome you all in the video lecture series of Analog IC Design, Analog IC CMOS Design. And here we have started our first unit, which is Basic MOS Device Physics. And this is our fourth lecture. And today we are going to see the second order effects in the MOSFET. So earlier we have discussed about the MOS device structure, as well as we have discussed about the threshold voltage, what is the impact of threshold voltage. And then we have seen the derivation of the MOSFET VI characteristics basically. So there we have seen the current equation in the cutoff, linear and saturation region. So that was the basic operation of MOS. We can call it as a ideal conditions, or we can call it as a first order effect. So first order effects means the normal working of the normal operation of the MOSFET. But here we are going to see the second order effects. Now, the first question is what is mean by ideal and the practical MOSFET. So here we will see that when we can call it as a MOSFET as ideal, and what is mean by the second order effects. So ideal MOSFET means we can consider as the constant threshold voltage. Threshold voltage, we already know that the minimum voltage required for the inversion of the channel means channel will get invert, or we can say channel is created at that particular voltage. So if there is a constant threshold voltage, we can call it as the MOSFET is an ideal MOSFET. Second condition, there is no zero channel length modulation. Now, what is mean by channel length modulation, that we will see here. So there is no channel length modulation effect, means the channel length modulation coefficient lambda is equals to 0. Then there is a uniform carrier mobility. There is no degradation of the carrier voltage. So there will be the uniformity in the mobility. Then there is a no velocity saturation also. So velocity will be in case the speed of the carrier or velocity of the carrier is also there is no change in the velocity, it will be constant. So these are the effects, or these are the conditions for the ideal MOSFET. But in reality, or in the practical cases, there are some effects which are appear in the normal operation. So that effects are called as secondary effects or second order effects. So these are basically we can say that these are the non-ideal phenomenon, or non-ideal physical phenomenon which causes the deviation from the ideal MOSFET. So whatever the ideal conditions we have discussed now, that it has a constant threshold voltage, then zero channel length modulation is not modulation is there, means there is no impact on the lambda. Then carrier mobility is also uniform. There is no velocity saturation also. So these are the ideal conditions. Apart from these ideal conditions, if there is any certain conditions happens, or physical phenomenon happens which is non-ideal one, so then we can call it as a second order effect. Now, what is the importance of these second order effects on the MOSFET? So it will affect the gain of the circuit, the gain of the MOSFET. We call it as gain, which is the ratio of output quantity upon input. So if it is a voltage gain, we can say that voltage output voltage upon input voltage. So it will affect the gain of the system. Then again, it will affect the speed. Speed also it will reduce because of these second order effects. Power and linearity also the major factor which can affect because of the second order. Then it is crucial in the analog IC design, because we are talking about the analog CMOS IC design. So whenever we want to find, check the analog IC design, or whenever we want to design the low power circuits, then these effects are very, very crucial. Even in the deep submicron CMOS technology also, these are the crucial factors. Then here in this lecture, we are going to discuss about the four second order effects in the MOSFET. So the first effect we are going to discuss is channel length modulation. So in short, we can call it as CLM. Now, what is mean by channel length modulation? So as we have discussed, what has happened in the linear region, what has happened in the saturation region. So this is the diagram or figure you can see over here. This is the NMOS, as here the source and drain are the heavily doped N-type region, and this is P-type body. So from this structure, we can able to see that this is nothing but the NMOS transistor. Now here you can see that this is the gate terminal, and as we already discussed that gate is the control terminal of the MOSFET. Whenever we want to apply the input, we will apply to the gate terminal. And you can see over here, this source terminal is connected to the body terminal. So in ideal conditions, we are connecting source terminal to the body terminal. So body terminal, we can also call it as substrate terminal. We can also call it as bulk terminal also. Now all these are P-type holes in this substrate region, and this N type means drain and source are diffused by the electrons, means N type. Now here you can see this is the dB, VDB. VDB is nothing but the drain to body voltage. Now here the actual length. Now this is the area in between source and drain. This is nothing but the channel. So here, as it is an N-type MOSFET, there is a channel created by the charge carriers, electrons, means negative charge carriers. Now here you can see that there is a depletion region formed near the drain, and here this is L. L is nothing but the actual length. This is actual length of the channel. Okay, when there is a no channel length modulation present. But when there is a channel length modulation, your L is nothing but change, and we can call it as L effective, means effective channel length. This is effective channel length. Okay, so up to this drain region, there is a L channel length, but now after depletion region, there is a depletion region formed. So because of that, we have taken this length as a LD, means depletion region length, and then the actual channel length is decreased by this measure. So here as we have seen in the saturation region earlier in VI characteristics, that MOSFET is ideally has a constant channel length L if in saturation region. Now when we are increasing the VDS beyond the VD sat, means now the we can call it as a VD sat, because our earlier voltage is VDS. VDS is nothing but the drain to source voltage. We can consider VDS as an output voltage. Now if, for example, in the saturation region, if this current, means ID, is independent of VDS, but now if further we increase the VDS, and we can call it as VDS sat, the depletion region at the drain widens, means there is a creation of diffusion region, and it will widens towards the source. Now here, if this widens, means your length of the channel will get reduced and it will pinch off. So this region, pinch off effect is also we have seen earlier. So this because of this pinch off effect, this channel length is getting reduced and reduced, and it will come towards the source. So now if you want to find out this channel length, it will be capital L, which is our actual length, and then delta L, which is nothing but this LD. So we can represent it as a delta L. So this is the length of the channel which is occupied by the depletion region. So if we want to find out the L effective now, it will be actual length minus the length of the depletion region. So it will basically shorten the channel, actual channel, means there is a less channel resistance. So definitely because of the less length of the channel, the ID will become increase again more. So ID will get increases. Now if you want to check what is the expression for the current or in the saturation region. So if there is a no CLM, if there is a no channel length modulation present, means there is no further increase of the VDS, then your equation will be like this: ID is equals to 1 by 2 mu n C ox W by L, VGS minus VT. Now earlier lecture we have seen that VGS minus VT is nothing but the overdrive voltage. This is overdrive voltage, and this L and W are the channel dimension or the MOSFET dimension. L is the length of the channel and W is the width of the gate. Where again Cox is nothing but the capacitance of the oxide layer, and mu n is the mobility. That N suffix is stands for the NMOS. So this is the square law which follows in the drain saturation region. Then in this case your current is independent of the VDS, but this is not the case in channel length modulation. This is when channel length modulation not there. Now here when we are considering the channel length modulation, when we are increasing the VDS further and when there is a formation of the depletion region beneath the drain, then your drain current equation will get changed. Now again for this we can call it as this is the non CLM case. We have to again multiply the term 1 plus lambda VDS when we are considering the CLM. Now this lambda is nothing but the channel length modulation coefficient or parameter. So this is CLM coefficient, channel length modulation coefficient. So now this lambda is completely based on the or depend on the VDS. So as VDS increases, lambda will get changed. Now what is the effect of this lambda? So this lambda is quantifies the strength of the CLM, means it will decide the strength of channel length modulation, and it will depends on the channel length, means L, and it will based on the process technology, which type of technology and how many processes or which processes are involved in the technology. That is that depends on that factor. This lambda depends. Again, if there is a short channel devices, means whatever the ideal conditions we have taken, that is long channel devices. But when we are considering the short channel devices, there are in this short channel devices, these second order effects are appear. So if there is a short channel devices, the lambda will be more, and in long channel devices, lambda will be smaller. Now if there is a CLM, then what is the output resistance? So if in ideal condition we can consider R0 is infinite, but if there is a CLM, then this output resistance depends upon the lambda and the ID. So the formula for this output resistance RO will become 1 upon lambda ID. So in ideal case it will be infinity, but in CLM case it will be 1 upon lambda ID. So here we have noted. So R0 is finite here, and I0 R0 is infinite if there is no CLM. Now second order effect we will discuss is body effect. Now body effect is also called as substrate bias effect. Now what is mean by body effect? So in the substrate region is also called as body, right? So here in this case also we have connected source terminal to the body terminal. So in ideal cases we are generally connecting body to the source terminal, but for example if we have changed the body voltage, or if we have applied some body voltage, whether it is negative, 0 or positive, then that will affect in the threshold voltage. Now for example, if the body effect we are considering, and if there is a depletion region forms by the effect of body, and so it will take more and more energy to form the channel, means it will increase the threshold voltage. So if there is no body effect, the threshold voltage required is less, and if there is a body effect, threshold voltage required is more to create the channel. So body effect we also called as substrate bias effect, which is refers to the change in the threshold voltage of MOSFET due to voltage difference between source and the body. So ideally if we keep source as a ground and a body is also ground, means both are in the same potential. But for example, if we keep source at the ground and if we apply body some voltage, then there is a voltage difference between the source and the body. So it will change the threshold voltage, and because of the threshold voltage, there is a whatever the voltage required for the formation of the channel, it will also change. Now why this body effect occurs? So there are the reasons when in MOSFET we are generally tying, as I told, ground, and if it is NMOS, and if it is PMOS, we are connected to the VDD. Now if source is not at the same potential as body, means there are different potential, then the voltage VSB, means source to body voltage, develops. So this change the depletion region width under the gate. Now, because of the depletion region, as I told, more depletion region charge, then higher gate voltage needed to form the channel. Means channel will get invert, but there will be a more chances to increase the threshold voltage. Then here we can consider. So the first case, we have applied negative bulk voltage. So if there is a negative bulk voltage, so here there is no change. But here, for example, if there is a we have applied 0 to the gate voltage, so there are, you can see that depletion here, depletion region forms. Again, if we are changing the body voltage, and if we create it, if we give the less body voltage, means less than 0, so again depletion, I'm changing this. So here this and this is nearly same. So here we have applied negative voltage to the, so because of the negative voltage, depletion region will be widened. So as depletion region wide, there we required more VTH, means more threshold voltage. So here if we include the body effect, then there is a change in the threshold voltage equation. So your threshold voltage will become now VT0. VT0 is nothing but threshold voltage when we are applying some VSB, or VSB is equals to VSB is equals to 0, and this is nothing but the complete body effect voltage, that is nothing but the VT. So VT0 means there is no body effect. Lambda is nothing but the, gamma is nothing but the body effect coefficient. Lambda is channel length modulation coefficient. Here gamma is body effect coefficient. Now here this phi f is nothing but the Fermi potential. So this part we have discussed in the semiconductor physics. So as I told you, if you have some basic knowledge of the semiconductor physics, so semiconductor physics is basically the prerequisite for this particular course. So if you have the basic idea, you will get the what is meant by Fermi level. So Fermi level we have already considered in the band gap theory. So this is the part of physics. So VSB is nothing but the voltage in between source and body, and minus again root 2 phi f. So this is the threshold voltage equation including body effect. Now again, if we have to find out the separate equation for the body effect coefficient, so it will be under root of 2q epsilon Si Na upon Cox, where Cox is nothing but the oxide capacitance, and this Q is the charge of electron. Then epsilon Si is the permittivity of silicon, and Na is the intrinsic doping concentration, higher doping. So, or we can say that substrate doping. The third second order effect is nothing but the subthreshold conduction. Now we have seen that when there is a channel formation, when the channel is inverted, so there that region we can call as strong inversion layer when we are considering that VGS is greater than or equal to VT. Now, for example, if there is, we have considered that whenever the VGS is less than VT, the MOSFET will be in the off state. But practically it has not happened. Subthreshold conduction is the phenomenon where MOSFET conducts a small but non-zero drain current. Very negligible drain current flows when the condition is VGS less than VT. Ideally, it should not be there. Current will be 0, but in the practical case, non-ideal case, it won't be 0. There is some leakage current flowing through the device when your VGS less than VT. So when device is theoretically off, but it is not when ideally or theoretically the MOSFET or the device will be in the off condition. So this region where the leakage current flows or a small amount of drain current flows through the device when VGS is less than VT, so that region is called as a weak inversion region. Now this is also called as subthreshold region. So another name is weak inversion region or subthreshold region. Now, in this case, the current equation again change when we are considering the subthreshold region. So, this I naught exponential VGS minus VT neta VT. So, here also this is the parameter in the subthreshold conduction. Fourth, we are considering the second order effects, which is DIBL. DIBL is a drain induced barrier lowering voltage effect, which is again a short channel effect. So whatever the second order effects we are considering now, these all are these all are a short channel effect, because in the long channel effect, the MOSFET operate very normally, and there is a negligible changes or negligible short channel effects are there. But in the short channel negligible channel modulation or DIBL or subthreshold conduction is there. But when we are considering the short channel effect, then these second order effects are more dominant, then they influenced more in the short channel cases. So what is mean by DIBL? So wherever there is a increase in the VDS, the source channel potential barrier it decreases. Means the potential required for the electrons or charge carriers to enter in the source region, that is very means conveniently they can enter in the region, because the potential will get reduced, barrier potential will get reduced. So this effect is called as drain induced barrier lowering. It is also because of the higher potential at the drain to source voltage. Now in the long channel MOSFET, the gate solely control the channel potential, but when the short channel devices came into the picture, the drain depletion region extends towards the source because of the pinch off effect, and higher VDS allows the drain electric field to influence the source barrier, means they can easily enter. So this reduces the energy barrier at the source end, and they are allowing the carriers to enter the channel more easily. So this is nothing but so it will again as a result of this, the transistor will get turned on even if the VGS is less than VT. In ideal condition, we will consider that when VGS is less than VT, the transistor will be in the off state. But because of the second order effects like DIBL and the earlier means subthreshold conduction, the transistor will get turned on. So these are all about the second order effect, and in the next video lecture, we'll see the another topic of this unit 1. Till then, thank you.